Morning. Here's your start to conic sections, and the namesake, of course you can see the word cone going on in there, but conic sections are, if you take a look at these pictures down below, they're really helpful. Conic pieces are things that are from a cone, so conic sections are sections of a cone depending on how you slice it. So imagine you had a ridiculously sharp knife of some kind and you chopped through now this cone at a particular angle. The very first slice that you can see at that angle, if it hits only one cone and you're able to pull off, part the cone into two pieces, looking at the cross section of it, you'd have what would be a parabola, that shape. It would be kind of a filled in version of this little thing you'd see right there. And then if you take and turn it and slice it exactly at 90 degrees to the cone and only hit one of the cone sections, and by the way, there's two sections to any cone, that's something to talk about here in a minute, but if you do it straight across, you get a circle is the cross section if you pull the pieces apart. If you catch one at an angle, kind of like you did with the parabola, but it gathers all of, kind of hit it just the right angle so it hits both ends, rather than having an open end that we did in the parabola, you'll get an elliptical type shape. And then finally, if you take a cone and slice it such that you hit both cones, and it can be perpendicular to it, it can be at a little bit of an angle, but if you hit both cones with your slice, then you get what's called a hyperbola. The cone itself is in two parts. We usually think of a cone as just being one section, like maybe the top half, but these are also infinite in size, so there's no end to the lengths of either end of this cone. They just keep going in both directions. We just cut it off for just conceptual sake so that you can see it. And we're used to seeing things that are just a single or a half of a cone. They call them like double cones or single cones. And I don't know if there's one like defined version of cone. I think you probably had to think of this double cone, which could mean there's like this. There's been like, I don't know, ice cream shops have had it out for us for years and only gave us half a cone. And you're welcome to make that argument the next time you stop off. But key features of any good old parabola is this thing called a focus and a directrix back here. And the focus is really the biggest part of it. It actually has a very physical ramification, something that we use all the time. So if you make, you guys have probably heard of parabolic microphones. So if you watch any sporting event, especially football, you see it a lot on the sidelines. But somebody's holding up what looks like a satellite dish. It's a two-dimensional parabolic microphone. All the sound that hits the edge of that microphone bounces off the edges and goes toward what you can see is like usually a little like rod sticking out with the microphone in the middle. All the sound that hits at a 90-degree angle or comes in at this, what I'm drawing right now, these red lines coming in, the sound entering all bounces off the sides and goes to that focal point, we call it. So it's like everything that enters goes to that focal point. It's like cupping your hand around your ears, and you hear things a little bit better. It's what happens is all the sound waves that would have passed your ear are now trapped by your hand and bounce back to your ear. And that parabolic microphone is doing the same thing, as it's capturing all the sound that's within an area, rather than just what traditionally you're going to hear is only what comes directly to it, and maybe some ambient sound around it, reflective. This amplifies it, and that's why you're able to hear things so far away, as it captures distant sound. Now that's parabolic microphone. This is the same property of satellite dishes as well, and that's why the bigger satellite dishes, they capture more minutia or things that are coming from a greater distance that are maybe faint or weak. Because a really weak sound, if you can capture a lot of it, or a weak signal of some kind that comes in, it might be really, 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 really faint. But if you capture a lot of it and reflect it all towards a single focal point, then the receptor, the microphone, can pick up that sound ably and all as well. So they're really cool properties, the parabolic microphone. Now that's the focal point. It's something that you can measure. Hey, Karen, can you turn that down, please? Thanks, buddy. They're watching a little TV. But that part is the thing we take notice of, and then the directrix, nice thing about that is the distance from the parabola's focal point to like an edge of the parabola. So if we're looking at, there's the focal point is, let's say 2 units away. The directrix will be the same distance away. The directrix is kind of like, it's a line that you would use to kind of steer that parabola. It's a line, I don't know if you want to call it perpendicular to, it's kind of hard to decide. It looks like it's tangent to, since we just talked about tangent lines, you know that concept. It would be tangent to the parabola if it were next to it, but it's not. It's back the same distance to the focal point is the same distance then to the directrix behind it. I think it was like kind of a rod that steers. If you were the parabolic microphone holder at the football game, you'd be holding onto the directrix to tilt it. Now, I'm going to delete all these little things that are on here, and then we'll kind of start fresh. But that gives you the idea of when you say focal points, it's actually a physical description of where all the sound or information that would enter that conic shape would bounce to a focal point. And what's boggling to me, and I think is super cool about these, is that we're just cutting slices of a cone, and every one of these has that property of focusing either a sound wave or some type of light wave or the ability to reflect to some kind of focal point. And that's from cutting a cone, which is bizarre in itself, and then all this relates to triangles, and then your world just implodes because you realize, oh, it's all related, which is super cool. The vertex thing, the other part of it is the vertex. I'm going to go and highlight that. So vertex is the point at the bottom of the parabola. We've talked about that before. Your standard parabola that we've seen for years, like x squared, that's one way to describe this, but we can also have them sideways, and the vertex is always and will forevermore be that kind of tip of the hill or bottom of the valley. So we'll call it HK because it often gets these funny letters H and K. So we call it H comma K, and you'll see it down below. If you kind of turn the pages in your notes, you'll see the H and K are used. Axis of symmetry. So in this case, if it's facing up and down, it's a vertical axis of symmetry, x equals h. So we all know that a parabola has symmetry about that vertex. It's equal pieces on both sides if you fold it in half. And then the focus is that point we just learned about, is somewhere in the middle. It's kind of in this direction. There's a way to measure and find it exactly, which is what we want. But there's a focal point in there, and we'll talk about how to label that in just a minute. And then the directrix is also involved, and that directrix we just talked about is that line that runs behind your parabola, in this case a horizontal line. The distance to the directrix and the focal point is always plus p. We call it a kind of just label it p for whatever reason, at least in our textbook, that distance is p. And if I move over to this side here, it's the same thing here. I'll adjust this hk for just a second. But this distance right here is also p, and then hk is the label for that. Okay, so that's just getting you some basics. Now we use those letters. There's actually a big box of information down below on how all those relate to each other. I'm actually going to shorten it quite a bit. Imagine that I usually have some kind of Mr. Seeley kind of modification that goes with these things. So hang with me. There is a neat property here on both sides of that focal point. You're going to find that there's 2p distance. So if you know the distance to the focal point, and then to the right and left of it, if you went 2p to the right or the left, you're going to hit the sides of that parabola. And what's nice about that is it kind of gives you a sense of scale. So if you know that p distance from vertex to the focal point, then you can also double that p distance right and left and land right on your parabola at those 2 points. Now those are, 3 total points on a parabola of infinite points, but they're really important points, and they give you a sense of scale of the parabola. Okay, so I'm going to put in there just p away from the focus, or from the vertex. And if I put it on your directrix, it would be like negative p away. And it's going to be a line. So it's facing up and down like this. It's going to be y. But I'm just going to leave it at that, because that give you guys a little sense of, I think you can do this more intuitively than just the formulas, and I'll show those to you in a minute. Okay, all of this is labeled really well. Make sure you've got that stuff, because the picture is worth 1,000 words in this case, and more importantly than usual. You got to draw all these things in here and label them in this picture. This is a sideways version of it, and so I want you to just see that if you space it left and right, that distance p is still the distance from vertex to the focus. We still call the vertex h and k, so we still label it the same way, hk, and it's still 2p from the focus to the edges of the parabola, left and right, so that's 2p up and that's 2p down. Remember, these are distances. When I label a p in there, that's what I'm referring to, a distance. All right, so that's all the big things that happen. Now down below, there's an equation, a way to write it if it's facing up or down with a vertex at a particular spot. So if it faces up or down, it has, if you think of in the old days, like we would have a parabola, think of y equals x squared was your traditional up and down parabola. Okay. And let me do another one, different color here. If you did x equals y squared, we did it, I think, once on maybe Demomo. We put it together one day. X equals y squared would be sideways. If you keep that frame of reference, it's easier to remember these formulas, because y minus k, and if I square that in my formula, I'm going to reference what's down here too. If you guys look down below the box on page 2, what I'm doing is I'm duplicating what's already on that page. But if I do y minus k, and I have an h minus k, and this one's going to face up and down, I'm sorry, an x minus h. If I want to establish a relationship between those, and this faces up or down, it's got to have this x being squared indicates that it's facing up and down. So in the formula, I'll notice this is squared, and the only difference, and then the y minus k portion of it will not be squared, because if it opens up or down, the x portion is squared, the y is not, and that's the key that you want to look for. It's not whether it's on the right or the left, whether it's squared or not. It's just that it has the x portion squared rather than the y portion squared, and it opens up and down. And then there's 4p. Now, that's a special form, a way of writing a parabolic or a quadratic equation. And if you put it in this form, what it makes evident is 4p. And you realize in all our drawings up here, the really important things to know for that parabola, hk and p. And so this is a form of writing that quadratic so that hk and p are made obvious. Now, we've written quadratics in, y equals x squared plus 3x minus 5, like standard form, the things that we've done in the past. But what we'll do here is we'll convert them so that we can rewrite it. And what we'll do is completing the square eventually, is we'll rewrite our equation so it looks like this that I've just written, so that we can find out that p distance, because that focal distance is really important, because we realize now it produces something that's actually kind of cool about a parabola, a focal point. Okay, so there's the p. That's just look in the picture and say, oh, there's p. I see that's the distance from the vertex to the focal point in the directrix, 2p to the left and right. H and k is the vertex, voila. Here's an equation form that I will algebraically be able to produce, or at least look at and identify stuff. If it's in that form, you actually can find p, h, and k. Okay. As an example, let me write one off to the side here. If I just said, hey, x minus 2 squared equals 12 times y minus 3, what that does is if you write it in that form, there's a lot of stuff that's apparently evident. You have, the vertex is at 2, 3. So from this example here, I'd go, the vertex is 2, 3. So I go vertex 2, 3. Okay, so I got that. It faces up and down because of the squared thing. Okay, so we're looking at that going, it's one of those up-down versions of it. And then we look at that 12 and go, that's 4p. So p has to be 3. That's the distance from the vertex. If it's at 2, 3, I'm going to go up 3 and down 3 to get my vertex and my directrix. Now, it can be up or down, and because this is positive 3, it faces up. So if it were a negative 3, this would face down. So that's actually another cool indicator, is that p follows the directions of, positive is up, negative is down. It's a focal distance, because this is for an up-down parabola. So if p is positive, the focal point is up, facing up parabola. If p is negative, it faces down. Okay, so that's the kind of information you get just from looking at that equation. You can almost say, I can picture this. I go to 2, 3, plot a point, and go up 3 to put a focal point, down 3, do a horizontal line. I can go from my focal point to the left, 2 times 3, so 6 to the left, to the right, 2 times 3. So I'm using all these things that you see up above here. Let me get it in yellow, and then I'll undo it. But all this stuff here I can create from that equation, and I can basically sketch out that parabola. All right, so that's a help. That's a start to this. I'm going to do the left-right version of it. So if you go over here, the left-right version,